So, welcome back, and let us see how the channel pattern changes because of the change in the slope, and how it affects the sediment bed load, and what different channel patterns evolve because of the change in the gradient and change in the discharge or change in the bed load supply in that particular basin. Okay. So, the channel patterns, if you look at this figure, then it shows that there are at least total 5 channel patterns, which ranges from straight, then you have straight with sandbars here, and then you are having meanders, then you have meanders, but at some locations you have wide channels here, and then you are having braided, and so on. Okay. Now, this also shows that the channel patterns will change, and which will comprise of different bed loads. So, mostly the straight channels will have suspended loads, whereas you have a mixed bed load and then coarser bed loads if you are talking about the braided channel pattern and all that. Let us look at that what it basically talks about. So, we have 5 basic channel pattern that exist. So, we have straight channels with either migrating sand waves, pattern 1, or we have the migrating alternate bars. So, we have this one, this is the pattern 2 with the sinus talvage, and then we have 2 types of sinus channels, 3A and 3B. So, where 3A is is showing highly sinus channel with equal width. So, the width remains the same throughout the channel along the valley. A channel which is wider at the bends. So, you are having the channels are comparatively wider at the bends than in crossing, and then you have the meandering and braided pattern. So, we have channel 4, the pattern 4, and then a typical braided stream, which has been shown here with the multiple channels and the channel bars in between. So, these are mostly the channels pattern which we will come across. So, rivers exhibits various channel patterns that can be related to: 1 is your variation in the water discharge. So, if you are having the variation in the water discharge, you will have the different channel pattern. Then variation in the sediment load, as we were talking here. So, you have the sediment load, suspended, mixed and bed load here. So, presence of bedrock also will affect the pattern to change. Okay. So, these are the few important points which will affect the patterns which we are talking about from 1 to 5. And then of course, is the human influence also plays an important role in altering the channel pattern, and the tectonic influence. Experimentally and in field research groups have studied and identified the local change in the channel pattern because of change in the slope. Okay. So, experimental relation between the valley slope you have and the sinuosity, which has been shown here, that so if you increase the slope, then you are having change in the channel pattern. If you are having, for example, straight, then you will have meander channel, and further if you change the slope, then you have the braided channels. So, the relative stability of these channels in terms of their shape and gradient are related to relative sediment size, load, velocity of flow and stream power. It has been possible to develop this pattern experimentally by varying the gradient, that is your the slope of the channel bed, sediment load, stream power, and the type of sediment load transport by the channel. So, either you are changing from the suspended to mixed load or bed load, then you will have different pattern of channel pattern you will come across. Okay. But here what has been shown is that if you change the slope, then you will get into the change in the sinuosity, that is, you are having straight, you will have meander, and then you will have braided. Following are the possible indicators of active tectonics that we usually look for on the local scale, that is the development of the meanders, local meanders. So, for example, if you are having straight channel and suddenly you are getting into the meander channels. Okay. So, that can also indicate some change, and then again it becomes straight. Okay. So, that what we were looking at in one of the slide in the previous lecture, that the topography which we had was something like uplifted here. So, we had a very tight meander here, and then we are getting into the slope down here, almost straight channels, okay, or less meandering, and here we were having very tight meander. So, this is also because of the change in the slope here. Okay. Local development of the meanders, or you can say local development of the braided streams or braided pattern can also indicate change in this local slope. Okay. And widening of or narrowing of the channel can also be taken as an indicator of possible indicator of active tectonics. Okay. But at the same time, we need to look at that or rule out the possibility of sediment flux coming in actually. So, whether it may be because of the increase in bed load can also change the channel pattern. Okay. So, that has to be looked into in detail before arriving to any conclusion that these are all tectonic indicators. But of course, yes, if you see this, then you have a question that why such change is been noticed in locally in the drainage basin. Then local development of ponds, okay, and this we were talking about when we discussed about the strike slip faults and all that. Okay. So, coming to again the same one. So, if you have the change in the gradient, so in order to maintain the constant gradient, the river bed that is being steepened by downstream tilt will cause increase in sinuosity. So, if there is an increase in if you are increase in slope, you are making the slope steeper, then you may have the change in the sinuosity, higher sinuosity, as it has been shown here. And similarly, if you are having reduction of the valley slope, will lead to reduction in sinuosity. Okay. Now, slight increase in the valley slope will shift the river pattern. If you consider this 5 river patterns which have been given here, so slight increase in valley slope will shift the river pattern from left to right. Okay. So, you will have, if you are having, if you increase the slope, okay, we are talking about the increase in valley slope, then we have from straight to meander and meander to braid. Okay. So, this is what has been shown here. So, you have from straight, you have to meander and meander to braid. So, with greater change of the valley slope results into incision and increase in sediment supply also. Okay. And that is change the mixed load channel to bed load channel. Okay. So, because if there is a change in the valley floor, it will, because of the increase in gradient, it will result into the incision in the area, and that will result into the increase in the bed load, and then bed load also will change from mixed load to coarser bed load. Now, a gradation and degradation response of a stream as it crosses the domes or faulted, that is uplifted area in the region. So, for example, if you are having, so this is the dotted line is showing the profile, the normal profile, and now if you try to uplift this, okay, then what will happen, this portion will be eroded. Okay. So, there will be an erosion here, whereas this portion will have deposition, and this portion will also have deposition. So, a gradation here, and degradation in the area of uplift. Similarly, you have, if you are having the profile, you have the downfall portion. Okay. So, you are having this portion is going down. So, the profile has new profile is here. So, it will again try to come back to this one. So, there will be an deposition here, whereas this portion will erode. Okay. So, this portion will get eroded, and further this will get filled up. So, deposition and erosion to maintain this profile. Okay. So, similarly was the case of here. Okay. So, it will try to maintain its profile. So, further in terms of the anticline and syncline, change in the channel pattern is caused by increase or decrease in the valley slope due to uplift or subsidence in the area. So, this has been shown at the anticlinal uplift. If you are having the meander, then it will remain as, but it changes further from meandered, braided to meander, and braided to slightly meander, and so on. Okay. So, the decrease, so this is basically the channel pattern is caused by that is change in the channel pattern is caused by increase or decrease in the valley flow. So, decrease in slope will cause the reverse braided to meander, to straight, or to anastomotion. Okay. So, this will be the change which will be followed, and vice versa, and this is what has been shown here, that you will have the changes. So, the most commonly observed stream adjustment is for a meandering channel. Okay. Increase in sinuosity in response to increase slope, decrease in sinuosity in response to decrease in slope. So, if we take this one here, this area, now I'll just discuss a little bit about this one. This is a Jwalamukhi thrust here, and this what I was talking here, this is an upward area, and the bias channel which is flowing across this here had shown us a very typical meandering pattern here, that we interpreted as an tectonic geomorphology indicator of ongoing tectonism. Okay. So, this is the portion here. So, the Jwalamukhi thrust runs over here. This portion is your anticline, and this is the upthrown side. So, as it crosses the anticline, before crossing it, and it shows a very tight meander. So, what you see here is straight meander to tight meanders, tightly incised meander, and then the sinuosity decreases here. Okay. So, you have the slope increases here, and then further the slope decreases here. Okay. So, you have it is crossing the topography, and this we took as an indicator for your tectonic activity. Some river channels undergo minor changes within the parameters without undergoing complete shift in pattern. Okay. So, for example, if you are having the uplift, which will result into the slope deformation. So, what we see is the uplift here. So, we have this portion will be a gradation, the uplifted portion will undergo erosion, and then a gradation here. So, what we see is that if you are having the braided meandering, then you have there is a formation of terraces, and the braided will change into meander, and then further if you are having the steepening of the slope here, then it goes into the braided channel. So, here because there will be lot of erosion, and slope is also steepened here. So, the bed load, the material will be more supply of material. So, bed load increases and the slope increases will result into the formation of braided channels here. And now, in case of subsidence, so this was in the case of uplift, and now looking at the subsidence. So, change in the Chelan profile which is subsided here. So, this forms an sort of a basin which will get aggraded. So, you will have the filling up of this portion, whereas this portion will get eroded. So, the gradation here, whereas here we see degradation, and it will have degradation on either side here. So, what pattern we will see is alternative bars here with terraces and braid bar here, again because this slope is steepening here, more of erosion, more sediment has been brought in, and so you will have braid bar similar to this one here and this one, and then further the gradient is reducing here, then we will have the alternate bars which has been seen like similar to this one. Okay. So, you will have the alternate bars and terraces, whereas here you will have the braided bar system. Now, the classical example, if you take the area from US New Madrid region, which shows a very interesting signature of the ongoing tectonic activity, and this area is the part of the intraplate region, where the region experiences a lot of microseismicity, and also they found that this area is deforming and this portion is upwarping slowly. So, let us see the details about this. So, this is from Mississippi River. So, this main channel is your Mississippi River here. So, the Mississippi River, when it crosses a 10 meter high topographic warp. So, this portion is the warped area, where you also see the occurrence of micro earthquakes and slightly moderate earthquakes with magnitude greater than 5, which has been marked here. Okay. So, this warp is caused due to active deformation in New Madrid seismic zone of Missouri. Here the Mississippi River reduces its sinuosity on the upstream side. So, the upstream side the sinuosity reduces of the uplift due to decrease in gradient, because this is uplifting. So, it is reducing the gradient. So, it will decrease the gradient, and increase in sinuosity is seen downstream. So, downstream the sinuosity increases because of increase in gradient. Okay. So, if you look at this one, so in the upstream what you are having, the channel floor has been raised. So, it has reduced the gradient. So, decrease in sinuosity, whereas here it has increased the gradient, that is increase in sinuosity. Such local development or variation in the channel pattern can be taken into consideration to identify the tectonic influence in the region. So, if we look in further detail of the Mississippi River, then this is what you will see, that there is a decrease in sinuosity, increase in sinuosity, and further you have the decrease in sinuosity for the नहीं वापस लेंगे इसको, ठीक है. So, if you look into the detail of the Mississippi River, then this what we have. So, the Mississippi River flows through the areas, shows change in the channel pattern due to tectonic movement. Okay. Above the uplift axis between, you are having, this is Cairo and the Hickman town, this is this one Hickman town here. The river is relatively straight. So, if you can see here, then you have a relatively straight channel here. And then however, in the downstream of this Hickman town, the river has high sinuosity, and this becomes a high sinuosity. So, you have the change in the channel pattern. Okay. So, the sinuosity is less, sinuosity increases, and then further the sinuosity is more. So, high sinuosity in the downstream side. Okay. This is what it shows here. Okay. So, you have the change in the sinuosity here. So, upstream of the uplift, this portion is your uplift here. So, the sinuosity is different here, sinuosity is different here, and different in the uplifted far. So, this is a classical example where it crosses the 10 meter high topographic bulge. Okay. So, low gradient reduces its sinuosity, on the up-dip flank of the uplift. So, it reduces the sinuosity and the up-dip flank, and where the gradient is lowered on the down-dip flank where the gradient are increased, the sinuosity increases. Okay. So, here the sinuosity increases. Okay. So, again increase in slope increases sinuosity, decrease in slope decreases the sinuosity. Now, looking at the another important parameter which you can use as an tectonic indicator is your stream gradient index. Okay. So, it is mostly what we are talking about, the stream gradient is the stream slope. So, if there is any local change in the stream gradient, that can be picked up by a simple equation and the parameters which you can extract from the change in the elevation and the total length for any particular point. Okay. So, SL is the is been given as, that is your stream gradient index, change in the elevation, change in length into total length. Okay. So, if you have you take the elevation and the distance and extract the longitudinal profile, and you want to measure the SL index at a given particular point at the center of these 2 points, then you are taking what the difference in the elevation here and the length here between the 2 points. So, this will give you the, that is your center which is what you want to study. Okay. And so, and then the total length. Okay. So, this is the change in the length, but this one is your, so there is a difference between the upper reaches and the lower reaches, and the elevation here you will get, that is the, and then the distance right from the divide, that will give you the L. Okay. So, stream gradient index is sensitive to rock resistance, to erosion and to uplift rate. With increased uplift rate, so you will have the higher values of SL if you are having increased uplift rate, and higher values of SL in rocks of relative low resistivity to erosion may be an indicator of recent vertical uplift. Okay. We also try to look at that what type of rocks the drainage basin through which the drainage flows. Okay. That also we will take into consideration. Now, this is a good example of from US again, where they took into consideration the SL stream gradient index. So, what they found was, so you have like different faults here marked by white lines, and the drainages which are, this is a rough sketch which shows the location of San Andreas fault and San Gabriel fault zone and Sierra Madre fault zone. So, what they found was high indices of SL were found along the southern. Okay. So, this marks the north. So, this is the southern portion and the eastern. Okay. So, southern and eastern portion of San Gabriel fault. Okay. So, they found higher SL indices here. Okay. So, higher SL indices. Okay. Now, both are the area of active faulting. So, along the southern side and the eastern side. Okay. So, high indices were observed along the Sierra fault zone, okay, which corresponds to 1971. Okay. So, 1971 earthquake, San Fernando earthquake. So, this was because of the earthquake. So, they were able to talk about that there was high SL values. Okay. Low indices were observed along the San Gabriel fault. Okay. So, that is what they are talking about. The south of this and the eastern side, they were able to see high SL indices, and they correlated this with the event of 1971, and then low indices were observed along the San Gabriel fault. So, high SL in the southern side and the eastern side, okay, were because of this one, and the low were observed along this one. However, though the San Andreas fault is active, low indices were observed. So, again you can talk about that a very recent event of 1971 was responsible in triggering the incision in this particular river along the streams. Okay. So, because again because and another reason which was been given here, that why we see less SL values along the San Andreas fault system, because it is an strike slip fault system. So, strike slip fault system are usually characterized by narrow valleys with crushed rocks, which can be easily eroded in the valley, which results into low stream gradient index. So, what is important here is that we need to look at that whether we are having the reverse fault system or a strike slip fault system, and even the fault is active. So, sometimes we will come across low stream gradient index because the movement is strike slip, whereas here the movement is reverse. Okay. So, this is reverse faulting, and here we are having the strike slip faulting. So, I will stop here and we will continue in the next lecture. Thank you so much.